A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You know how everyone seems to think that every time a big AI lab like OpenAI or Anthropic drops a new flagship model, they just wipe the slate clean and start from scratch? Like they have this giant, empty digital brain, and they just start pouring the entire internet into it all over again? It is this image of a pristine white room where a scientist hits a button labeled New Model and waits 6 months for the progress bar to hit 100%.
Herman Poppleberry here, and corn, that is the very misconception we need to dismantle today. It is a persistent myth. This idea that every few months or every year, these companies just hit a big red reset button and spend another $100 million on electricity just to relearn that the sky is blue and the capital of France is Paris. It is a fundamental misunderstanding of how the industry has evolved.
It really is a strategic liability at this point. If you are a lab and you are starting from zero for every trillion parameter model, you are basically setting money on fire. Our friend and housemate Daniel was asking about this the other day. He has been playing around with fine-tuning whisper checkpoints for some audio projects, and he wanted to know if that iterative process he is using has any resemblance to what the big players are doing at the frontier. He was curious if the checkpoint logic he uses on his local machine scales up to the massive clusters we see in places like Redmond or San Francisco.
Daniel's question hits on the fundamental economic and technical reality of AI in 2026. We are past the era of monolithic one-off training runs. We are now firmly in the era of what we call continual pre-training. If you are not doing this, you are probably going to go bankrupt trying to keep up with the scaling laws. The sheer physics of data and compute have forced the industry to move away from the event-based training model towards something much more fluid.
Precisely. The cost of training a model with over 1 trillion parameters from a cold start is now upwards of $100 million in compute alone. That does not even count the data engineering, the human feedback, or the massive talent costs. So, today we are going to pull back the curtain on how these labs actually iterate. We are moving from training as an event to training as a continuous biological style evolution. We are going to look at how these models grow, how they are surgically altered, and why the release date is becoming a bit of a legacy concept.
And just to set the stage, we should clarify some terminology because it gets messy. Most developers are familiar with fine-tuning, where you take a finished model and give it a little nudge toward a specific task. You are essentially painting the front door of a house. But what the big labs are doing is something much more invasive and complex. They are performing what I like to call weight surgery. It is not just adding a layer of paint, it is adding a new wing to the house while people are still living in it, without the roof collapsing.
Weight surgery. That is a vivid term. It sounds like something out of a science fiction novel, but it is the literal reality of how you scale a model without losing what it already knows. So, Herman, let's break this down for Daniel and everyone else. If I have a model that is already smart, and I want to make it twice as big and 10 times more capable, how do I actually start that process without losing the reasoning abilities it already has? How do we avoid the blank slate problem?
Well, the first thing you have to look at is the difference between checkpoint warm starting and true continual pre-training. Warm starting is the simpler version. Imagine you have a model that is already halfway through its training. You can take that snapshot, that checkpoint, and just keep feeding it more data. You are essentially resuming a paused download. But the real magic happens when you want to change the architecture itself. You want to change the shape of the brain.
Right, because you are not just adding more data to the same bucket. Sometimes you need a bigger bucket. You need more hidden dimensions, more layers, or maybe you want to move to a completely different structure. Like the Sparse Mixture of Experts architecture that really took over the industry back in February of this year. That was a huge turning point.
It was the turning point. In February 2026, we saw a massive industry-wide pivot towards Sparse Mixture of Experts, or SMOE, as the primary architecture for iterative scaling. Before that, models were mostly dense, meaning every part of the model worked on every single word or token. But with SMOE, you have specialized experts within the model. When you want to iterate, you don't have to retrain the whole thing. You can add new experts or lobes to the brain.
So let's talk about that surgery. When a lab wants to expand a model, they do not just add random neurons. They use techniques to expand the embedding layers and the hidden dimensions of the existing neural network. How do you actually grow a matrix?
One common way is to literally copy or split the existing weights. This is often called net initialization. If you have a weight matrix that represents a specific concept, say the concept of gravity, you can duplicate it and add a tiny bit of noise to the new version. Initially, the two versions do the exact same thing. But as you start the new training phase, they begin to diverge. One might stay focused on basic physics, while the other starts to specialize in general relativity. This way, the model starts its new training phase with all its previous knowledge intact, but it suddenly has more capacity to learn nuances it couldn't fit into its smaller brain before.
So it is like taking a brain and suddenly giving every neuron a twin, and then telling those twins they can go off and learn their own hobbies.
In a way, yes, but it is more about expanding the mathematical space. If the model was previously forced to compress its understanding of quantum physics and its understanding of baking recipes into the same small set of parameters, the expansion gives those concepts more room to breathe. They can diverge and become more specialized. But the trick is doing this without causing what we call catastrophic forgetting. This is the nightmare scenario for any AI researcher.
That is the big one. I remember we touched on this back in episode 974 when we were looking at emergent logic. If you start training a model on a bunch of new medical data, how do you stop it from forgetting how to write Python code or how to be polite to a user? It is like learning a new language and suddenly forgetting your native tongue.
That is the $100 million question. Labs use a few different strategies to prevent this. One of the most effective is called elastic weight consolidation, or EWC. Think of it like a protective coating on certain parts of the brain. The training algorithm uses something called the Fisher information matrix to identify which weights are most critical for the skills the model already has. When the new training starts, it places a higher penalty on changing those specific weights. It says, you can learn all about this new cardiovascular research, but you are not allowed to significantly alter the parts of your network that handle basic syntax or logical deduction.
It sounds like a balancing act. You want the model to be plastic enough to learn new things, but rigid enough to hold on to its foundation. It is like being a student who is open-minded, but doesn't want to forget everything they learned in grade school.
Precisely. And another huge part of this is the replay buffer. This is something Daniel might recognize from smaller scale work, but at the lab level it is massive. As they are feeding the model new, high-quality 2026 data, they are constantly mixing in a small percentage of the original training data from years ago. It is like a constant refresher course. The model is learning about the latest geopolitical shifts in the Middle East, but every few steps it has to solve a basic calculus problem or summarize a classic novel just to make sure those pathways stay active. They call this interleaving.
The curriculum learning aspect of this is compelling. From what I have seen in recent research, labs are becoming much more intentional about the order in which they introduce new information during these second and third phases of pre-training. They aren't just dumping a bucket of data, they are designing a syllabus. They are treating the model like it is going through a master's degree after finishing its undergraduate studies.
They really are. In the initial pre-training, it is all about broad exposure. You want the model to see everything, the good, the bad, and the weird parts of the internet. But in these iterative leaps, like what we saw with the transition from the base GPT-4 to the 4.0 architecture, the curriculum is highly optimized. They might focus heavily on multimodal integration early in the update, teaching the model how to relate visual tokens to text tokens before moving into deeper reasoning tasks.
Let's talk about that 4.0 example for a second. That was a huge shift, because it wasn't just a bigger version of the previous model. It was a fundamental change in how the model handled different types of input natively. How does weight surgery work when you are trying to stitch together a vision model and a text model that were previously separate? That seems like trying to sew a bird's wing onto a mammal.
That was one of the most impressive engineering feats of the last few years. Instead of just having a vision encoder that talks to a language model through a bottleneck, they effectively merged the hidden spaces. They used a technique where they initialized the new multimodal parameters using the existing text-only weights as a foundation. By doing that, the model didn't have to learn what a dog was all over again, it just had to learn how to map the visual pattern of a dog onto the linguistic concept of a dog it already possessed. It is much more efficient than training a multimodal model from zero. It is about creating a shared latent space where sight and sound and text all live together.
It makes me wonder about the trade-offs, though. If you are always building on top of an old foundation, do you eventually run into a ceiling? If the original architecture had some fundamental flaw or bias in how it organized information, can you ever really scrub that out with continual pre-training? Or are you just building a skyscraper on a slightly tilted foundation? At some point, don't you have to tear it down and start over?
That is an astute point, Korn. There is definitely a risk of technical debt in the weights themselves. Some labs have found that after 3 or 4 generations of continual updates, the model starts to become less efficient. The internal representations get cluttered. It is like a computer that has had too many software updates without a clean install. That is often when they decide to do a distilled rebake. They will take all the knowledge from their best continually trained model and use it to supervise a brand new, clean slate training run for a smaller, more efficient model. It is like taking all the notes from a disorganized but brilliant student and rewriting them into a perfect textbook.
So even the clean slates are not really clean. They are distilled versions of the previous generations. It is evolution, just at a hyper-accelerated pace. I want to pivot a bit to the internal logic here. When we look at these trillion parameter models, the sheer scale makes it hard to predict how an update will affect reasoning. Does adding more parameters through weight surgery actually improve the logic? Or does it just make the model a better parrot? Does the reasoning part of the brain grow, or just the memory part?
That is where the data mixture problem comes in. In 2026, the ratio of synthetic data to human curated data has shifted dramatically. In the early days, we were afraid of the model collapsing if it ate its own tail. The model collapse theory where AI learning from AI leads to stupidity. But now we are seeing that highly curated, high-quality synthetic data is actually better for teaching reasoning than the messy, contradictory data you find on the open internet.
Right? And we talked about this in episode 5084 regarding autonomous AI research. If you can use a smaller, highly specialized model to generate 1,000,000 perfect examples of logical chains, step-by-step reasoning for math or code, and then use those to warm start your next giant flagship model, the reasoning leap can be massive. It is not just about more parameters, it is about the density of the signal in the training data. We are moving from quantity of data to quality of reasoning chains.
And that is a huge differentiator between the big labs right now. Look at the difference between the Anthropic approach and the OpenAI approach. Anthropic has always been very focused on constitutional AI and RLHF, which is reinforcement learning from human feedback. Their iterative updates often feel very focused on safety, alignment, and a specific type of helpful, cautious personality. They are using their updates to refine the moral and logical constraints of the model. It is like they are raising a very well-behaved, thoughtful child.
Whereas OpenAI seems much more focused on raw compute-heavy scaling, their updates often feel like they are pushing the boundaries of what the hardware can handle. They're the ones really leaning into that sparse mixture of experts model we mentioned. By making the model sparse, they can actually add more parameters without increasing the compute cost of every single token. You might have a 2 trillion parameter model, but only a few hundred billion are active at any given time. It is about efficiency through specialization.
Spot on. And that makes the iterative process so much easier. If you want to make the model smarter at coding, you can just add a few new expert layers specifically trained on the latest programming languages and integrate them into the existing mixture of expert structure. You do not have to retrain the whole brain, you just add a new specialized lobe. This modularity is what allows them to move so fast. They are essentially hot-swapping parts of the model's intelligence.
That is a compelling way to think about it. But it brings us back to the user side of things, which I think is where Daniel's question really hits home. If these models are living organisms that are constantly being updated and surgically altered, what does that mean for the people building on top of them? We talked about the AI deprecation trap in episode 808, and this seems like the technical root of that problem. If the brain is constantly changing, how do I know my app will still work tomorrow?
It absolutely is the root. When a lab performs weight surgery or changes the data mixture in a continual pre-training run, the reasoning patterns of the model can shift in subtle ways. Even if the benchmark scores go up, the specific way the model handles a complex prompt might change. For a developer, that is a nightmare. Your perfectly engineered prompt might suddenly stop working because the model's internal priority for certain tokens has shifted. It is like the ground is constantly moving under your feet.
It is like the model is undergoing a personality change while you are trying to have a conversation with it. So, if I am a developer, how am I supposed to handle this? If I know the model I'm using today is just a checkpoint in a never-ending training run, how do I build something stable? Is there such a thing as a stable version anymore?
The first step is to stop treating model versions as static artifacts. You have to treat them as moving targets. One thing we are seeing successful teams do is build their own internal evaluation suites that focus on reasoning patterns rather than just outputs. You need to know not just if the model got the answer right, but if it used the same logical path it used yesterday. You need to be running unit tests for the model's logic every single day.
That makes a lot of sense. You are basically building a diagnostic tool for the model's brain. If the lab does a major update and you see the logical pathing start to drift, you know you need to adjust your integration. But let's go deeper on the reasoning versus knowledge balance. When labs do these incremental improvements, is it easier to add knowledge or to improve reasoning? I would assume knowledge is just a matter of feeding it more books, but reasoning feels more fundamental.
Knowledge is relatively easy. That is what we see with basic fine-tuning or even just extended pre-training. You can feed a model 1,000 medical journals and it will become a better medical assistant. But improving the underlying reasoning, the ability to take two unrelated facts and synthesize a new conclusion, that is much harder to do iteratively. That usually requires a significant change in the data mixture or a very careful application of reinforcement learning. It requires teaching the model how to think, not just what to know.
It feels like there is a limit to how much you can improve reasoning through weight surgery alone. At some point, you probably do need an architectural breakthrough. But we are seeing that these sparse mixture of experts models are surprisingly flexible. They seem to allow for these leaps in reasoning by letting the model dedicate more specialized compute to difficult problems. It is like the model learns when to think harder about a specific prompt.
They do, and the efficiency gains are wild. We mentioned earlier that warm starting can reduce training time by 40 to 60%. Think about the scale of that. If a full training run takes 6 months and costs $100 million, and you can get the same results in 3 months for $50 million by starting from a previous checkpoint, that is a massive competitive advantage. It allows these labs to iterate twice as fast as someone starting from scratch. It is the difference between releasing one major update a year and releasing 4.
It also means the barrier to entry for new players is becoming almost insurmountable. If you do not have a high-quality base model to start your surgery on, you are starting so far behind the curve. It is not just a compute race anymore. It is a weight heritage race. The lineage of your model's weights is becoming its most valuable intellectual property. You can't just buy 1,000 GPUs and catch up. You need the years of experience baked into those weights.
Weight heritage. That is a powerful concept. It really highlights why the open source versus closed source debate is so intense. If a company like Meta releases the weights for a massive model, they aren't just giving away a tool, they are giving away years of foundational training that anyone else can now use as a starting point for their own surgery. They are giving away the DNA of the model.
It is definitely a different world than it was even 2 years ago. I want to go back to something you said about the mixture of experts and the February shift. Why was that such a turning point for iterative scaling? Was it just about the money, or was there a technical breakthrough?
Before that, most models were dense. Every parameter was used for every calculation. If you wanted to make a dense model bigger, you had to retrain almost everything because the information was so diffused throughout the network. It was like a giant ball of yarn. You couldn't pull one string without moving the whole thing. But with Sparse Mixture of Experts, the information is more localized. This modularity is the key to iteration. You can update the router, which decides which experts to use, or you can update individual experts without touching the rest. It turned the model into a collection of plugins rather than a single solid block of granite.
So it really is becoming more like a software project. You have different modules, you have version control, and you have these massive integration phases. I can see why Daniel was asking if it looks like his Whisper fine-tuning. On a conceptual level, it does. It is all about building on what came before, but the engineering required to do it at a trillion parameter scale is just mind-boggling. The orchestration alone must be a nightmare.
It really is. Making sure that thousands of GPUs are perfectly synchronized as they perform these weight updates is a feat of engineering that we don't talk about enough. If one server has a slight lag or a memory error during a surgery phase, it can corrupt the entire model. You are essentially performing open heart surgery on a patient that is spread across 3 different data centers.
And then you have just wasted $10 million of electricity in a single afternoon. No pressure, right? One bad line of code and you have turned your flagship model into a very expensive random number generator.
You nailed it. And this is where the autonomous agents we talked about in episode 5084 come back in. At this scale, humans can't monitor every variable. We are now using AI to monitor the training of AI. We have specialized agents that look at the loss curves in real time and say, hey, this part of the weight surgery is causing the model to lose its ability to understand sarcasm. We need to adjust the data mixture immediately. It is a closed-loop system of self-improvement.
That is the ultimate meta-commentary on the state of the industry. We are building brains so complex that we need other brains to help us build them. It really makes me wonder where this ends. Do we eventually reach a point where the models are never finished? Where there is no such thing as a release date, just a continuous stream of updates, like a social media feed, but for intelligence?
I think we are already there, Korn. Think about how we use these models now. We don't wait for the next big version as much as we just notice the current one getting better over time. The labs are constantly pushing small delta updates to their live models. It is a continuous evolution. The idea of a model being finished is becoming an obsolete concept. It is a living, breathing digital organism that is being fed and groomed every single day.
It is a bit unsettling if you think about it too long, but for the developers and the users, it means we are always at the cutting edge, whether we like it or not. I think we should talk about some practical takeaways here. If this is the reality of AI development in 2026, what should our listeners be doing differently? How do you survive in a world of living software?
The biggest takeaway is to stop building for a specific model checkpoint. If you are fine-tuning your own small model or building an application on a large one, you have to build for the underlying reasoning capability, not the specific quirks of a version, because those quirks will change. The weights are going to undergo surgery, the data mixture is going to shift, and if your application relies on a very specific, fragile prompt, it will break. You need to build reasoning, robust systems.
So, robustness is the name of the game. You need to test your systems against multiple versions and look for the logical invariants. What are the things the model always gets right, regardless of the update? Build your core functionality on those invariants. Don't rely on the model's current mood or its specific way of phrasing things today.
And don't be afraid to do your own small-scale version of this. If you are a developer like Daniel, look into how you can use warm starting for your own specialized tasks. You don't always need to start your fine-tuning from the base model. If you have already trained a model on a similar task, use those weights as your starting point. It saves time, saves money, and often leads to better results because you are building on a more relevant foundation. You are creating your own weight heritage.
Another thing I would add is to pay attention to the model's drift. If you are using a major API, you should be running regular benchmarks on your own specific use cases. Don't just trust the lab's general benchmark scores. Their version of beta might not be your version of beta. If they did weight surgery to improve coding and it accidentally made the model slightly worse at creative writing, you need to know that before your users do. You have to be your own quality assurance department.
That is a crucial observation, and it connects back to that AI deprecation trap we keep mentioning. The labs are under immense pressure to keep scaling, and sometimes they make trade-offs that don't favor every niche use case. You have to be your own advocate in this iterative world. You have to be the one saying, hey, this update actually broke my specific logic chain.
It is remarkable to think that we have moved from a world of static software to a world of evolving intelligence. It really changes the fundamental nature of engineering. It is less about building a bridge and more about tending a garden. You are trying to guide the growth of something that you don't fully control. You are a gardener of weights and biases.
I love that analogy, Cord. Tending a digital garden. It is much more organic than the old way of thinking. And as these models get bigger and more complex, the gardening is only going to get more difficult. But the rewards are incredible. We are seeing reasoning leaps that were unthinkable just a few years ago, all because we figured out how to build on top of our previous successes instead of starting over. We are standing on the shoulders of our own previous checkpoints.
It is a testament to human ingenuity and a lot of very expensive hardware. But at the end of the day, it is the math and the strategy that make it work. The surgery, the replay buffers, the elastic consolidation. These are the tools of the modern digital architect. It is not just about more data, it is about better integration.
And it is only going to get more wild from here. We are already seeing research into modular architectures where you can hot swap entire sections of a model's brain while it is still running. Imagine an AI that can learn a new language in seconds by simply downloading a new expert module and integrating it into its mixture of experts. That is the direction we are headed. A truly plug-and-play intelligence.
The end of the model release era. It is a big shift to wrap your head around, but I think it is a more honest way to think about intelligence. Our own brains don't have release versions. We are just a continuous stream of updates and experiences. We don't wake up as Corn version 2.0. We just wake up as a slightly more experienced version of ourselves. Why should our AI be any different?
You have got it. We are finally building machines that learn the way we do, bit by bit, building on the past and always evolving. It is a messy, expensive, complicated process, but it is the only way to reach the kind of frontier intelligence we are all chasing. It is the path from calculators to colleagues.
Well, this has been a deep one. I feel like we have covered a lot of ground, from the economics of $100 million training runs to the surgical precision of weight duplication. Daniel, I hope that answers your question about how the big labs are doing it. It is like your whisper fine-tuning, just with about 12 more zeros on the end of the parameter count, and a team of 100 engineers acting as digital neurosurgeons.
It really is the ultimate engineering challenge of our time. And if you are listening to this and finding it as compelling as we do, we would really appreciate it if you could leave us a review on your podcast app or on Spotify. It genuinely helps the show reach more people who are interested in these deep dives into the weird world of AI. We are trying to grow our own listener heritage here.
Yeah, it makes a big difference for us. And remember, you can find all our past episodes, including the ones we mentioned today, at our website, myweirdprompts.com. We have a full archive there, and you can even send in your own prompts if you have a topic you want us to dig into. We love the technical ones like this.
We love getting those prompts. They always push us to look at things from a new angle. So, keep them coming. We are always ready for more weight surgery on our own understanding of the world.
Definitely. Well, Herman, I think that is a wrap for episode 1049. I'm going to go think about my own weight surgery. Maybe I can duplicate the part of my brain that remembers where I put my keys. I could use a few more experts in that particular lobe.
Good luck with that, Corn. I think you might need a distilled rebake for that one. Your internal representations are looking a bit cluttered.
Fair enough. Thanks for listening, everyone. This has been my Weird Prompts.
Until next time.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from sloss